Now what we would like to do is we would like to continue with our discussion of failure criteria. We've already considered a criteria for brittle materials. Now we're going to consider next two criteria that is meant for ductile materials. And the two criteria are sort of building upon each other. And the first one is the easier one, so that's what I'm going to cover. So the name of the criterion is very similar to the name that we suggested for the brittle material, but there are essentially two changes that reflect the fact that we're working with a ductile material. So the name is the maximum shear stress yield criterion. So first I should probably highlight that this criterion has an alternative name that we should also definitely remember. And in fact, the name Tresca criterion is probably used more often than the maximum shear stress yield criterion. Now, I see two keywords here. The first one is the word yield. And because I see the word yield, I know that this is meant for ductile materials because brittle materials have little or no yielding. And in an idealized world, no yielding at all. The second keyword I see is the maximum shear stress. Okay, so I'm gonna now make use of these keywords and formulate the failure criterion. The name itself suggests what I'm supposed to do. Now, before I say that, we should keep in mind that the phrasing of the failure criterion is actually reflecting the physics of the problem. Now, you're going to learn more about the physics of why materials fail and deform in your material science class. But let me summarize, although we're also going to talk about it just a tiny bit in the next topic, in the following topics on stress-strain curve. Now, if we have a brittle material, the way it fails is you break the bonds within neighboring atoms. So there is little local motion of the atoms, little local deformation. It's just that you stretch the bonds elastically and then you essentially rupture them. So therefore, you end up with almost a ideally atomically flat fracture surface, and therefore the signature of a brittle failure is a very nice, smooth, sharp, and bright surface. So that's what you would see in the case of brittle failure, and that's why how the surfaces of fractured glass essentially, for instance, look like. When you talk about ductile failure, you're talking about plasticity, significant deformation, and that's mediated by dislocations, moving, locally deforming the atomic lattice, and ending up with large deformations of the interface zone. And dislocation motion, it turns out, is mediated by shear stresses. So the name of the criterion is essentially reflected ultimately or motivated by the physics of the problem, and it's very suggestive of what we are supposed to do. So what are we supposed to do? What we are supposed to do is calculate the maximum shear stress and check against yielding. So we can first put it into a generic form that is not in the form of the stencil, because I won't be directly working in terms of the principal stresses to calculate the equivalent normal stress, but I will use another form that I briefly commented upon earlier, and then I will put it in the stencil form. So what I want to do is I want to calculate first of all an equivalent shear stress. That's in general the idea, even with shear stresses, and compare it against a critical value of the shear stress that can be sustained in the structure. What is the equivalent shear stress? Well, the equivalent shear stress is the maximum shear stress that I find at a point in the structure on any plane that I can look at. So I look at many planes at a point, and the maximum one I encounter is the absolute maximum shear stress. So essentially, this quantity is equal to tau max, as we've called it before, the absolute maximum shear stress. Now, the absolute maximum shear stress, I know, is a function of the principal stresses. And that is essentially what we have said before. Why is it a function of the principal stresses? Well, because the absolute maximum shear stress can actually be formulated as such. The absolute maximum shear stress is the maximum of the difference between sigma 1 and sigma 2. So when we draw the Mohr circle, there will be three principal shear stresses, and they can be formulated as the differences of the principal normal stresses divided by 2, sigma 2 minus sigma 3 divided by 2, and sigma 3 minus sigma 1 divided by 2. Okay? So the maximum of the shear stresses on every Mohr circle with respect to the principal values is the absolute maximum shear stress. And notice that the equivalent shear stress is therefore representable in terms of the principal stresses. And that's what I said earlier. Ultimately, we go from the general stress state to the principal picture because the principal stresses alone determine everything ultimately that we would like to know about eventually failure. So the equivalent stress that I am seeking, shear stress, is the absolute maximum shear stress. Good. So I know that part, and I know exactly how to calculate it as soon as I know what the principal picture is. The question is now, what is the critical value that I should be comparing it against, right? So now at this point, let me give you a hint and pause. This criterion is supposed to work for very complicated states of stress with all conceivable values of sigma 1, sigma 2, and sigma 3. Now, therefore, it should probably work for a very simple scenario such as uniaxial loading. If it doesn't work for uniaxial loading, then it will probably not work for any more complicated scenario. So having said that, can you find out what the value of the critical shear stress should be in terms of what we know from a uniaxial tension test, which is the yield strength? So I would suggest that you pause for a few seconds and think about that, but let me give you the answer. If we do a uniaxial tension test, we would eventually calculate a state of stress that is essentially one that has only one principal stress, which is, say, sigma 1, and failure occurs if sigma 1 is equal to the yield strength. The other two principal stresses, sigma 2 and sigma 3, are both 0 in a uniaxial tension test. So the only Mohr circle that we have is this Mohr circle. And therefore, the material, if the material is failing because the absolute maximum shear stress reaches a critical value, and simultaneously I am in the uniaxial tension test observing yielding, this must be the critical value that the material is able to sustain. And that critical value is exactly equal to the radius of the circle, which is sigma naught over 2. So the critical value is sigma naught over 2. So just like we did in the simpler case of the brittle fracture criterion, in this case, what we are doing is again referring to the uniaxial tension test, and we are extracting the piece of information we need from that test. So, in my opinion, this is the simplest way to remember the maximum shear stress yield criterion, or the Trescott criterion. We find the absolute maximum shear stress. For uniaxial tension test, this is what it is. But in general, we will have multiple principal stresses. We just go ahead and find the absolute maximum shear stress compared against the critical value, which I can always think about and find or identify to be sigma naught over 2. Now, having said this, and having observed that no matter what you do, eventually the equivalent stress or the formulation of the criterion is in terms of the principal stresses, let me go ahead and try to put this in the stencil form, which is not hard at all. All I have to do is I observe that there is a factor of 2 here and there as well as in the critical stress. So I will go ahead and multiply everything through 2 and end up with the stencil form. The stencil form, remember, says that, well, you put the principal stresses into a function, okay? And now that function is specific to the maximum shear stress criterion. So why don't I put a subscript S to remind me of that? And now I know what that function is going to be. I have multiplied everything through 2. It's going to be the maximum of sigma 1 minus sigma 2, no division by 2, sigma 2 minus sigma 3, and sigma 3 minus sigma 1. And that ends up giving me, in terms of the stencil, now not an equivalent shear, but in our usual form, the equivalent normal stress. I'll put again a S to indicate that this is for this criterion. And I'm going to compare it against some critical value, and that critical value is simply the yield strength. Okay? So what I said before is that the material property may not go in exactly as it is, because for the shear formulation of the criterion in terms of shear, it goes in as the critical shear stress or the yield strength for shear, which is sigma naught over 2. So it's scaled by a factor of 2. But in terms of the normal, in terms of normal stresses, equivalent normal stress, it is still sigma naught. And that is the stencil form that we had proposed earlier. This is not hard to remember either. Practically, I personally find that easier to remember and apply. Now, what is the safety factor? It doesn't matter if you use the principal stresses or eventually the normal stresses, equivalent normal or shear stress. You'll end up with the same safety factor, because both the critical value and the quantities that go into the criterion are simply scaled here through a factor of 2. So no matter what you do, the safety factor will be the same. It doesn't matter how you think about it. And that safety factor is simply the ratio of the yield strength divided by the equivalent normal stress for the Tresca criterion. Okay, so now the next issue of concern, as we've done previously, is to go ahead and try to visualize this criterion. And the nice way to do that is to remember or apply a state of plane stress. So I'm going to again assume that sigma 3 is equal to 0. When sigma 3 is equal to 0, this criterion takes the form sigma bar S equals the maximum of sigma 1 minus sigma 2 of sigma 2 and of sigma 1. Okay? And we will go ahead and try to plot that. In the space of loading, which is where I can vary sigma 1 and sigma 2. Remember, it's a complicated state of loading. I'm converting it into the principal picture, so I have only, in this case, 2 degrees of freedom due to plane stress. So now I'd like to find the locus of points that eventually have to do with failure, and I'd like to see what it looks like. So let me go ahead and start. So I will start from a state of 0 stress, and I will first move along the one direction, and I want to find out how much I can move. Well, if sigma 2 is 0, only the absolute value of sigma 1 matters, so the furthest I can move is simply the value of the yield strength. So that's the furthest I can move in that direction. Same thing goes along that direction, along this direction, and also that direction. Okay, then as I've done before, I will draw a line that has a slope of 1. Okay, and now if I am below this line, and what I'm doing is I'm going to take a state where sigma 1 and sigma 2 are both non-zero, and I start from the value 0, 0, and I proportionally increase both of them, and I try to increase the state of loading, the criticality of the loading, until I hit a point where failure occurs. So when I do that, so first of all, notice that sigma 1 is larger than sigma 2 below the green line. So 1 is larger than 2. Both are positive, so the value that dominates is this one. So in other words, the farthest I can go is, again, sigma naught. So if I'm below the green line, this is the furthest I can go. If I'm above the green line, now the value of sigma 2 will dominate, and it turns out the same thing happens in the third quadrant as well. Now, however, if I'm in that quadrant, something slightly different happens. In this quadrant, and alternatively in the other quadrant, what we see is that the values of sigma 1 and sigma 2 are different. So one of them is positive, the other one is negative. So when I take their difference, their difference will have a value that is larger than these two. So it's this thing that eventually will dominate. So in this particular case, sigma 2 is negative. So what eventually will cause failure is the difference of sigma 1 minus sigma 2. And when that is equal to sigma naught, then failure will occur because this essentially is equal to sigma bar s. Okay, so I try to find the points that eventually have to satisfy this equality. It's just a line. Think of this as x and y equals a constant. It's the equation of a line. And this line passes through 0 sigma naught, so that point, minus sigma naught 0, so that point, and in between is just a line. So that is the failure surface in that portion. In that portion, that's how it's going to look. Okay, so that's the way the failure surface looks for the Tresca criterion. So if I load, when I hit this, if I'm inside the surface, I'm safe. If I'm on the surface, I'm about to fail, and I am not permitted to be outside. If my design indicates that my stress state lies outside, it's a bad design. I need to go back and revise it. And remember, in this fashion that we're thinking, it's always easy to formulate the safety factor in a slightly different way. We can visualize it as such. Suppose I'm moving along that line, and I am at this stage of loading, and the distance, the length of this line is essentially, let's say, d. Now, the total distance that I can actually go is that distance, which I can visually easily determine. So that distance, let's say, is ds, the absolute maximum distance that is allowed with this criterion, that is the Tresca criterion. So the safety factor would be the distance I've moved along my loading line, which divides ds. So the safety factor at that point is going to be equal to ds divided by d. Okay. Now notice that safety factor, because of the triangle geometry, is the value of sigma 1, which divides sigma naught. So it's sigma naught over sigma 1, and sigma 1 in this region is the value of sigma bar s. So it's essentially the same form, it's just a geometric representation. Now, one final remark. These surfaces hold for sigma 3 equals 0. What if sigma 3 is not 0? It turns out if sigma 3 is not 0, well, the surface will be three-dimensional. Essentially, you will imagine that there is a sigma 3 axis that moves out of the plane. And now, if I load the structure in a direction, in the 1, 2, 3, in the three-dimensional space of sigma 1, 2, and 3, I want to find out how much I can move in a certain direction and away from the paper until I hit failure. Okay? And the locus of all points that lead to failure constitutes a surface which is going to be in 3D, and it will have a certain orientation. So now those pictures you can easily find in your book, but let me just mention what it is for the previous criterion so that you can make an analogy in some sense with this criterion. The previous criterion was the maximum normal stress criterion. In that case, the analogy would be that, well, if this is the case for sigma 3, in all directions I'm looking at the principal maximum value of the principal stress, which is equal to sigma u, the ultimate strength. If I apply a stress in the third direction as well, the farthest I can go is also sigma u. And if I compress, also sigma u. So if it's a square in 2D, in 3D, it will be a cube. If you lie in the cube, you're safe. Outside, you have failed. So in this case, the surfaces will look different, but ultimately you can go ahead and think about that and see the pictures in the book. So the question is this a good criterion? Now, the extent again depends on whether we are able to replicate experimental data. Now remember, this criterion is predicting failure that occurs on the plane with maximum shear stress. For uniaxial tension test, the orientation, the physical orientation of this plane is at a degree of 45 degrees with respect to the axis of loading. Okay, so when I take a brittle specimen, we had observed that the maximum failure is the maximum normal plane, more normal stress plane, which is the perpendicular to the axis of loading. So a ductile criterion indicates that it should be at an angle of 45 degrees. So here it is. for a steel specimen. Okay. Now, steel specimen, we've performed the tension test. Now, there are several things to talk about this tension test. We're going to talk about it in the lab more and also in the discussion of the stress-strain curve. But essentially, what you're seeing here is the following. We pull, and of course, the specimen will experience some plastic deformation, but also you notice that there is this gauge portion where we eventually monitor the stresses and the strains, but that gauge portion ultimately thins down as we're about to fail. So if you look from above, you can notice that there's some significant thinning in these portions and on the left as well. That is called necking. And that is where the stress-strain curve starts to eventually, when it forms, it starts to dip down. Now, and then the material fails, okay? Now, the necking thing is a phenomena on its own, but it's not quite I would say it has to do with the material property, but it doesn't quite have to do with the way the material fails. What has to do with the material failure is the way that failure surface is oriented. So now, if I rotate this specimen, and if you're able to view the failure surface, you can see that it's not a flat surface. In fact, there are planes of angle. There are multiple planes where maximum shear stress is reached. This is one, that is one, that would have been one, this 45 degree would have been one. Any plane with 45 degree orientation essentially works. So in this case, we see those planes forming and the material deforming, failing on those surfaces of orientation 45 degrees, which have apparently to do with the maximum shear stress. So maximum shear stress is indeed the mediator of failure for ductile materials such as the steel. And here is another failed specimen. And in this case, you can see as well that this failure surface is at a certain angle, which actually looks very close to 45 degrees. Now, is it exactly 45? This is the idealization. This says that it should be 45 degrees, but in practice, of course, it might be slightly different. Okay, so that is the discussion of the maximum shear stress yield criterion. And what we are going to do next is solve a couple of examples.